The final talk in the session is on fast temporal convolutions for real-time audio signal processing, and the talk is given by Stepan, Miklanek, and the co-author is Jiri Schimmel. Welcome back.
Okay, I'm from University of Technology in Brno, and I would like to present to you our results today. First of all, I would like to do some quick introduction and motivation which fueled this paper. As some of you maybe are familiar with the temporal convolutional networks, which were successfully used for guitar amplifier modeling, for modeling of dynamic range compressors and some other nonlinear devices. And although the temporal convolutional networks are quite a universal tool for modeling of these types of devices, their main disadvantage is that they are really computationally expensive. And especially when we compare them, for example, with the recurrent neural networks composed by gated recurrent units or the long short-term memory units, we can see that the RNNs are actually much more suitable for applications in real-time signal processing. So the main motivation of this paper is that can we actually optimize the convolution layers, and can we approach similar processing speeds as with the RNNs? In this paper, we are talking about discrete causal convolutions, meaning that these type of convolutions are only dependent on previous time samples. And we are also introducing a dilation factor, which actually allows us to skip some of the previous values of the previous time signal. And we do that to gain a larger time context for or a reception field. And this is especially helpful when building temporal convolutional networks from these type of layers, because when we stack together a multiple or a large number of these layers, we can get actually a quite large reception field, which is useful when modeling stateful systems. In our work, we've experimented with two implementations of the real-time buffering system, and the first one is a simple single buffer, and the second one is actually the double buffered state. The obvious difference between these two approaches is that the first one actually does one memory write per time step, and the second one does two memory writes per time step. Although this doesn't introduce quite a computational overhead when you're dealing with one-channel convolutions, in TCNs or with this type of neural networks, we are dealing with multi-channel convolutions. So in our approach, we've decided to go with the first one. We've actually implemented two versions of these algorithms, and we've experimented with statically and dynamically allocated variables inside of these layers. And this thing was actually proposed or suggested in previous work by Chetan Chaudhary. And as you may know, or the main disadvantage of this approach when using the statically allocated variables is that after changing or after initializing these layers, they actually cannot be changed at runtime. This means that if you construct a neural network from this type of layers, you are only limited just to a single structure, and nothing can be changed later when using it, for example, in a VST plugin or a standalone application. But the main advantage of this approach is that we can actually gain quite a computational speed up with this approach. And just to make things clear, the computations in our approach are actually done with some of the built-in functions from the Eigen library for C++. The algorithm works quite simply. First of all, we store the input channels in a given position in the memory, which is given by the right pointer. And then we must read particular positions in memory which are given by the read pointers. And the read pointers are actually different each time when we use a different lengths of the kernels, and also the dilation factor extends the memory needed for these operations. Then we can store the selected memory columns in the memory and perform a simple element-wise product with the filter weights, which we've previously gained by training a neural network. And one of the last steps is we then perform a sum of all of the elements in the resulting matrix, and then we insert, then we gain just one output sample, which we then store in some kind of output channel array. And this process is, of course, repeated several times because we are dealing with multi-channel convolutions. To evaluate our results, we've actually re-implemented one of the previously proposed models, which is based on WaveNet-style architecture. And this model is actually composed of stacks of convolutional blocks with multi-channel convolutions. And also in the inner structure, there are also so-called gated activations, which are built from two nonlinearities, specifically the hyperbolic tangent and the logistical sigmoid function. The one specific thing about the TCNs is that they are using very short kernels. So in this sense, it is feasible to implement these convolutions in the time domain instead of, for example, the frequency domain. We've actually, in our work, we compared previous custom implementation of the convolution layers. And the first one is WaveNet Virtual Analog, which was previously proposed in 2019. And the second one is actually comes from a community-based project, which is called RT-Neural. In our approach or in our measurements, we've actually measured how long it takes. How long it takes to process 1 second of audio, and the processing speed was actually measured as a real-time, as a factor of requirement for real-time use, meaning that if the factor was larger than 1, then the system or the model or convolutional layer was able to process the signal in real time or faster. And all of the measurements were actually done at a sampling rate of 44.1 kilohertz, as was the case in some of the previous works. The first thing is that in ideal situation, the dilation rate should not affect the processing speed. And this was the first thing we noticed when trying to measure different implementation, including ours. And so, for example, the RT-Neural version is dependent on increasing the dilation rate, and this results in lowering the processing speed every time you extend the convolutional kernel or increase the dilation rate. And therefore, we've discovered that this type of approach isn't really suitable for building the TCN models because they are usually using really high dilation rates. And when we look at some of the other results, we can see that in some cases the RT-Neural approach is actually faster than ours. And this is due to the fact that we've actually, when I was talking about static allocation, even though in our static version of these layers, we are using static allocation for the variables, we've actually decided to use dynamically allocated memory in these layers. And this is because we've experienced some stack overflows when trying to allocate memory for the convolution layers with large dilation factors, which actually require a pretty large memory. Now, for the comparison of the TCN models, we can see that, and by the way, this was actually compared to the WaveNet virtual analog approach. We can see that our dynamic TCN models were not drastically faster than the previous approach, and the speed up ranged from approximately 2 to 3 times faster processing speeds. But on the other hand, the static implementation resulted in quite bigger improvement, and the speed up range approximately from 2 to 12.8 faster processing times, of course, depending on the selected architecture. We've also selected from some models with different hyperparameters, and by the hyperparameters I mean the different number of layers and channels. And with these examples, we can see that the processing speed was improved to 6.2 times faster than the reference. One interesting thing to note is that when you look at the bottom top and the bottom table, you can actually see that the TCN2 model, despite having more layers, actually performed better than the TCN1. And this is due to the fact that the static allocation is actually the most performant when using smaller variables, which is the case for the TCN model. And when you look at the reference, this actually doesn't apply for the reference models. And the last thing, we've also compared these kind of models with the RNNs, which were also successfully used for virtual analog modeling and modeling of nonlinear systems. And the first thing that can come to your mind is how we can even compare these types of neural networks when they are completely different in structure. And from previous work, we are familiar with we know that these kind of models actually produce similar perceptual results. So in this way, we can actually roughly compare also the processing speed. And when we look at the reference times for the RNNs, we can actually see that our implementation or the TCNs is really comparable to the RNNs composed by the Jiri units and LSTM units. And in some cases, the TCNs can actually get faster than the RNNs, or at least compared to the previously proposed times. And to make this comparison better, we also implemented our version of the RNNs. But then we discovered that our implementation is actually faster than the previous one, although we could not compare the reference implementation of the RNNs because the implementation isn't available. So we could not figure out why this was the case. But as a result, this makes some of the TCN models actually slower again. So this is just one thing to note. And I think the main takeaway from this is that a static allocation of variables is the most beneficial with smaller number of channels, or with the TCN with smaller number of channels. So to give you some conclusions and future directions, we've actually proven that it is possible to approach similar processing speeds as with the RNNs. But as you've seen, this wasn't the case every time. And at least I think that the proposed algorithm can be used, for example, in other variations of TCNs. And perhaps some variation of TCNs can be actually used to model linear systems. And the last remark is that there may be future room for improving or modifying the TCN blocks which are actually present in these kind of structures. So this is the end of my presentation. I would like to thank you for your attention, and feel free to answer any of your questions. Thank you.
Thank you very much, Stepanek. Questions, please.
Hi. Yeah, first, thanks for the talk. probably super relevant for my work also, since I've been using TCN models based on Joshua D. Rice's research recently. Question one would be, is there any code of your TCN block implementation already published?
Yes, I totally forgot about it, but it's available on GitHub, and the link is in the paper.
Okay, then I have not seen it when skimming over it, but okay, good to know.
Although the only block that is implemented is actually the one with the gated activations, but I'm sure it can be easily modified. So.
Yeah, that can be modified, I guess. Yeah. Yeah, and second question would be, how would you characterize the main modification that you're doing with the now single block design, single buffer design that you used, I guess? Was it correct?
When I was looking at the original implementation, it actually uses a similar type of approach of just the one single buffer.
Exactly.
But I mentioned the double buffered state because it is implemented in the RT-neural library. So at first I was trying to compare these two approaches and their advantages. But actually it is really similar to the previous approach, this buffering.
Yeah, and how would you characterize your main modification then? Is it similar to a grouped convolution, or how can I interpret that? I haven't had enough time to digest actually what you've shown at the presenter.
The main difference is that the original implementation uses a lot more for loops and code which actually can slow down this type of buffering. Or at least I think this is the case. But the main speed up of this implementation actually comes from the static allocation of memory. I don't think there is much benefit from or much difference in processing speed in the buffering side of things.
I see. Okay. Yeah, good to know. Thanks.
Thank you.
Okay, there's one.
The implementation is for GPU or for CPU?
All the computations are done on the CPU.
Okay.
Okay, then let's thank Stepanek once again for his talk.
Thank you.